Hello everyone, so welcome back to the good stuff that we've been doing. Today in this video we're going to look at a very nice problem from the International Mathematics Olympiad from 1959. Here the problem says that we should prove that for all integers n, that is for all natural numbers n, integers, that this fraction, which is 21n plus 4 all divided by 14n plus 3, is irreducible. Now this is what this actually means by irreducible. They mean that expressions like, let's say 5 over 4, or let's say 3 over 7, or 12 over 15, these expressions, for this case, there is no way we can divide 5 and 4 by any number, so we cannot reduce it further, so it is irreducible. For 3 and 7, there is no way we can divide 3 and 7 by any number, so it is irreducible. But for 12 and 15, we can always divide this by 3 and divide this by 3 to get 5, so this will give us 3 over 5. So we will be able to reduce 12 over 15, but we are unable to reduce 5 over 4 and 3 over 7. So in this case here, this expression is reducible, but this 2 is not. Now we are told that we should prove that these fractions of this form, let's consider the fractions n equals to 1, you get 21 plus 4, so this is 29 over 14 plus 3, that is 17, yeah. And for n equals to 2, you get 21 times 2 will be 42 plus 4, that is 46 over 14 times 2, that is 28 plus 3, 31. So these two cases here, now you can observe that this fraction, there's no way you can divide any of them by any number to reduce it further. For the first case here, 29 and 17 are both primes. For the second case, one is even, so one is odd. Now we are told that we are to prove that this will be the case even for n equals to 3, even for n equals to 1000, or n equals to even a million. That if you plug this n here and any fraction you get, that you cannot reduce it further. And this is one of the things that make me love number theory a lot. The problems are always easy, but the implications are so mind-boggling. Like, it's so, like, for all n, these expressions, like, just tell me that you cannot reduce this further, it's even amazing. Though the solution is easy, like, it's easy to solve actually, but just that the problem alone is very beautiful. That's what I mean. So let's go back to our work and ask ourselves, how do we prove these statements? But let me take this off and we can examine it further. So the question now is that, how do we prove these statements? Well, I'll prepare some basic tool in number theory. Assume that a divides an integer b and a divides an integer c as well. Then a must divide a linear combination of b and c, that is, a must divide bx plus cy. So a must have to divide a linear combination of b and c. And why is this the case? Well, this is true because if a divides b, it means that a should divide bx. Obviously, if 2 can divide 6, 2 should be able to divide 12 and 18. That's what this means. So a should be able to divide bx, and if a can divide c, then this means that a should be able to divide cy. This means that a should be able to divide bx plus cy. No, notice that we can add them up because a can divide b and a can divide c, so we can always factor out a from these two expressions and we will get a division, like the quotient will be an integer. So like this case now, any number that will divide 21, let's say k, if k divides 21n, okay, that is 21n. If k can divide 21n plus 4 and k can divide 14n plus 3, then obviously k should divide the linear combination of these two expressions, right? But how do we form the linear combination? Well, we should choose x and y such that n cancels out. Well, let's factor out, let me take this part out, and let's try to factor out for the first part 21. Okay, so 21 is 7 times 3, I believe, and 14 should be 7 times 2. So if I multiply this guy by 2 and multiply this guy by 3, they should give you the same number. So in this case, if we subtract, we should get a 0 times n. So that means I have to I have to multiply 21 by 2. So in this case I have to multiply this by 2. So k should be able to divide 2 times 21n. Let me write it where. 2 times 21n plus 4 minus 3 times that is 14n plus 3. So notice that in this case now the n's cancels out and we get 2 times 4, that is k should be able to divide 8 minus 9, which implies that k should be able to divide -1. But k dividing -1 means that k should be equals to 1. So in this case, these two numbers, 21n plus 4 or 14n plus 3, the only numbers that can divide the numerator and the denominator is actually k equals to 1 or k equals to -1. But that means that they don't have a common factor, because for example 3/7, the only number that can divide both of them is just 1 or maybe -1. So they don't have a common factor. That is what it means. So this case now, that means we have proved that for all values of n, this fraction cannot be reduced further. This is what we have proved. And observe that if you are given similar problems in the future, maybe you are asked to like evaluate, let me say 3n plus 7 and 15n plus 2. You are asked to maybe prove that this expression is irreducible, or if it find the factors or whatever. Actually, you can actually do this. Any number can divide 3n plus 7 and 15n plus 2 should be able to divide their linear combination. So that number should be able to divide 5 times 3n, so that is 5 times 3n plus 7 minus maybe 15n plus 2 this way. So that number should be able to divide 5 times 7 minus 2, so that is 35 minus 2, that is 33. Then our k should be able to divide 33, which means k should divide 3 and k should divide 11. So that means 11 and 3 should be able to divide this fraction. You understand? 11 and okay, that means 11 and 3 should be able to divide this fraction here, this expression. Let's set n equals to 1. So n equals to 1, this should be 10/15 plus 2, that is 17. So that would be okay. So that would be 10/17. This would not have a common divisor, but notice that what k divides 11, k divides 3 actually means is that any number that should divide these two expressions should be able to divide 3 and 11. Like 3 and should be able to divide 3 and 11, but one can divide 3 and 11. But that means that at some point this expression should have a form that 3 and 11 can divide. That's what it means. That any number, like we may get some forms whereby it is maybe like 3/5, but at least some time we will be able to get a fraction whereby 3 and 11 can be able to cancel out. That is what this theory means. So this fraction is not irreducible for all n, but it is irreducible for some n. But this case, this one is a very strong case for our, like, it's a very strong case whereby it is not possible to be reduced further. So thank you for watching the channel, and please do subscribe to the channel. Please do subscribe. Thank you.